Good morning. All right, I want to talk, before we get into 6.4, I want to talk a little bit about 6.1, the beginning of your packet. Now that we've done a little bit of work with the properties of exponents, I want to talk about what is an exponential function. So an exponential function, by definition, is something in the form, I'm just going to write some notes out on here, in the form of y equals a times b to the x. Now, you've seen a few functions and you've experimented with a few functions like y equals 2 to the x, or y equals 3 to the x, or y equals 1/2 to the x. Now notice these are all technically in this form. They don't have an a value. I mean, they actually do have an a value, but you don't see it there. So for this one right here, your a value is equal to 1 and your b value is equal to 2. For this one, your a value is equal to 1, your b value is equal to 3. Here, your a value is equal to 1, your b value is equal to 1/2. But you could also have something like y equals 5 times 2 to the x, where a would equal 5 and b would equal 2. Okay, so I'm going to give you a couple examples. If we had a couple ordered pairs and we knew our function was exponential, so you could write it like this, you could write it as function notation. Either way, I kind of use these interchangeably. Okay, let's say we had two ordered pairs. Let's say we have 0, 2 and 2, 50. And you were asked to write an exponential equation in this form for a function or a graph going through these two ordered pairs. Okay, now I'm going to show something that works out really nicely in this example. We'll call this example number 1. Okay, so you've got y equals a times b to the x. Let's plug in the first ordered pair. 2 for y equals a times b to the 0. Now something really nice happens here. We know that something will be to the 0. Anything to the 0 is going to be 1. So that kind of goes away because it's just 1, and 1 times a is just a. So a is equal to 2. Okay, so now our equation, y equals a times b to the x, is y equals 2 times b to the x. Now we can plug in the other ordered pair. The y value is 50 equals 2 times b to the x. X is 2. Divide by 2, 25 equals b squared, so b should equal plus or minus 5. But by definition, your base of your exponential function must be positive. B must be positive by definition. So we know that b is not plus or minus 5. It's always going to be, it'll be the positive 5. So your function is y equals a, which we found up here to be 2, times b to the x. And there's our exponential function that passes through these two ordered pairs. Now I'm going to give you a second example that doesn't work out quite as nicely. Let's say you have two ordered pairs, 2, 7, and 4, 63. I shouldn't say it doesn't work out as nicely. It does work out as nicely. It's just you don't have this bonus where the x value is 0. So right away you plug in one ordered pair and you've got one of your two unknowns, one of your two constants. This one's going to take a little bit more, a couple more steps. So y equals a times b to the x. Let's plug in the first ordered pair. And 7 is the y value. A times b squared. Okay, notice we didn't get rid of anything. We don't know a or b by plugging in just one. Let's plug this one in. Y equals a times b to the x. We'll plug in the 63 for y equals a times b to the x, b to the 4th. Okay, so now we've got two equations, two unknowns. I'm simply going to solve for, let's solve for a. A is equal to 7 over b squared. So I can use substitution. I'll plug that in over here. 63 equals 7 over b squared times b to the 4th. 63 equals b's reduced to b squared, so 7b squared. Divide by 7. 9 equals b squared. B equals plus or minus 3, but again, your base has to be positive in an exponential function, so b is 3. Now we can come over here. A is equal to 7 over b squared, 3 squared, or we know b squared is 9. So now we've got a and b, and we've got our equation y equals a times b to the x, or y equals 7/9 times 3 to the x. And there's our exponential equation. Okay, now with that background, let's go back to that front page. Okay, this page right here, and talk about the rabbit problem. Exponential functions differ from quadratic functions of the last chapter. Remember a quadratic function, something like y equals ax squared plus bx plus c. That was quadratic in standard form. Notice there were exponents, but your exponents were constants. The exponent was a 1 here, it was a 2 here and a 1 here. Okay, and exponential functions differ because the variable is in the exponent. It's called an exponential function, not just because there's an exponent somewhere, but because by definition, your variable's in the exponent, which makes it an exponential function. Exponential functions make reasonable mathematical models for unrestricted population growth. When somebody says something grows exponentially, it's growing really, really quickly at an increasing rate. Every time you add a constant, so here's a property to an exponential function we're going to look at a little more closely later in the chapter. But every time you add a constant to x, you multiply y by a constant. Okay? Let's look at the rabbit problem. Okay? Let's just jump right in. When rabbits were first brought to Australia in the 19th century, they had no enemies, so their numbers increased rapidly. Assuming that there were 60,000 rabbits in 1865, and that by 1867, 2 years later, the number had increased to 2.4 million. Assume the number of rabbits increases exponentially with the number of years that have elapsed since 1865. So we're defining 1865 as year 0. That's going to help us quite a bit. Okay. So let's look at what we're doing here. And I'm going to put this on another sheet of paper because we don't have a ton of room here. Okay. So let's define our variables. Number of rabbits increases exponentially with the number of years. So y increases exponentially with x. So y is the number of rabbits, increases with x. X is the number of years after or since 1865. So if we look at our ordered pairs, there were this many rabbits in 1865. Well, our ordered pair, 1865 is 0 years after 1865, so we have 0, 60,000. Remember, when our x value is 0, that made it a little bit easier, gave us one less step when we're solving for this equation. Our next one is in 1867, so that's 2 years after 1865, and we had increased to 2,400, 000. That's our y coordinate. Okay, so let's come up with our equation. Y equals a times b to the x. So if we look at this, we're trying to do this in 4 different ways. We want to represent this in 4 different ways. So we're going to do our best to do that. Let's first do algebraically. We want to come up with an algebraic equation for this. Here's our algebraic equation. We just have to solve for our 2 constants a and b. Let's plug in the first one. The y value is 60,000 equals a times b to the x to the 0. Well, that's nice. The b to the 0 is 1. That goes away. So we have 60,000 equals a. So let's go. Now we know a is 60,000. 60,000 times b to the x. And let's plug in the other one. Our y value is this. 2,400,000 equals 60,000 times b to the x, divide by 60,000, divide by 60,000, b to the x is equal to 40. Oh, sorry, that's not b to the x. We know we're plugging in a 2 for x, so b squared. Remember, we plugged in, sorry, we don't plug it into this step, b to the x. So in this step, we're plugging in this for y, and we're plugging in this for x, so b squared. So b squared is now equal to this divided by 60,000, which is 40. So b squared equals 40, or b equals rad 40, which we could simplify to 2 rad 10. Okay, now our equation is y equals a 60,000 times 2 rad 10 to the x. Okay, so that's representing this algebraically. Y equals 60,000 2 rad 10 to the x. Okay, now let's look at numerically. Well, numerically we said there's a property. So we have a year and we have number of rabbits. There was a property, every time you add a constant to x, you multiply y by a constant. So we have the year 1865. We had 60,000 rabbits. 1867, we had 2,400,000 rabbits. So we added 2 to the x. And what did we do here? 60,000 times what is 24 or 2.4 million? We multiplied by 40. You just take this divided by this, you get 40. Okay, so if we add 2 more years, this is just a way to look at it numerically. So by 1869, then we'd multiply this by 40. Remember, every time we add a constant to x, we're multiplying the y by a constant. And here we get 96 million. So I multiplied 2.4 million by 40 and we get 96 million. Let's just do one more. Plus 2. So that's going to be 1871. Multiply by 40. We're going to run out of space here. We have 3,840,000,000 rabbits. Okay? So there were no enemies. So these grew exponentially. At some point, this can't continue. But while it's growing exponentially, it's following this model. Okay? Verbally, what we can say here is every 2 years, the number of rabbits multiplies by 40. So this is all the same function. We can represent it algebraically. We can represent it numerically. We can represent it verbally. And then graphically, we can make a graph. Okay? Let's make this be the number of years, years after 1865. And this will be number of rabbits on the y-axis. You could do this on your calculator. I actually just entered this on the calculator, and we could do, it looks kind of like this, okay? If you do a menu 5-1, so at year 0, you get 60,000. At year 1, you're at 379,000. At year 2, you're at 24 million. Year 3, you're at 15 million. Year 4, we're at 96 million, and so on. Okay, so this is kind of hard to graph, but you're going to have 60,000 somewhere around here, and it's growing exponentially. So you're 1, 2, 3, 4. Year 2, oh gosh. So this is just going up really quickly. Okay, it's hard to do that and draw a scale there, but you could represent it graphically. Okay, one more thing I want to quickly look at is the other side. So this page, y equals a times b to the x. If you look at this function, kind of a fairly simple function, complete the table in the graph for this graph. So when x is 5, you have 2 to the 5th, which is 32. When x is 4, 2 to the 4th is 16. When x is 3, you have 2 to the 3rd, 2 squared, 2 to the 2nd, 2 to the 0, 2 to the -1, 2 to the -2, 2 to the -3, 2 to the negative 4. Now notice what happens. This kind of goes backwards. Normally we make a table and the values are going up. But look at what happens. That same property holds. Every time you add 1 to the x, you're multiplying your y's by a constant. So times 2, add 1, multiply by 2, okay, and so on. What do you notice about the pattern of the x values? Actually, let's graph this real quick. 0, 1, 1, 2, 2, 4, 3, 8, negative 1, 1/2, 1/4, 1/8. Well, notice these are going to get closer and closer to the x-axis, but they don't cross it. So we're going to make that a dotted line to show that we never cross that dotted line. We get infinitely close to it, but we never touch it. Okay? Pattern of the x values. What we notice is every time you add 1 to the x's, or you're adding 1 to the x's, so you're adding 1. Notice about the y's, you're multiplying by 2. That's if you look at these going downwards. Now, if you think of it the other way, if you're subtracting 1, then you're dividing by 2. Or we're going to say instead of saying you divide by 2, we're going to say we're multiplying by 1/2. And I'm not going to say subtracting 1. I'm going to say adding a negative 1. This way, that pattern we talked about on the first page, where every time you add something to the x's, you're multiplying the y's by a constant. So you're adding negative 1 if you go downwards, and you're multiplying by 1/2 as you go this way. Okay, so you could think about it either way. Okay, what happens when the b number is something other than 2? Okay, so you could check these out. When the b number is something other than 2, it might not grow quite as quickly. If it's less than 2, if it's bigger than 2, it's going to grow even faster. Like our last one where our b value was rad 40, that's a lot bigger than 2. What do you notice about the y-intercepts of all three graphs? Well, your y-intercept is always 1. If you look at all of those, the y-intercept is always 1. Okay. In fact, your y-intercept, it's not always 1 because on this graph that we did on the other side, the y-intercept wasn't 1. It was 60,000. The y-intercept is actually always your a value. Okay, if you think about that, that makes sense because when your y-intercept happens when x is 0, and when x is 0, you've got b to the 0, this part goes away. Okay, and your y value is just going to be a. So for these graphs, your a was 1, so your y-intercept will always be 1, and a is 1. Okay, let's say y-intercept is your a value. What does the negative axis seem? How does the negative x-axis seem to be related to your graph? Looks like the negative x-axis, your graph is coming closer and closer to that x-axis. Okay, and that is called an asymptote. When a graph approaches but does not touch a line, any line, but in our case, the x-axis, okay, it's called an asymptote. The word comes from the Greek asymptotes, meaning not due to coincide, because you approach it, but you never touch it. Okay, the function is increasing when b is greater than 1, and decreasing when b is between 0 and 1. So you might have graphed something like this. And if you graph something like this, your graph is not increasing. Y-intercept is still 1, but it's coming down this way. Your x-axis is still your asymptote. You're still never going to touch it, but it's decreasing going left to right instead of increasing going left to right. Okay? And this is all assuming your A value is positive. Okay? And that's all for now.